So, hi guys. First we want to do a little bit of focus here. And what we'll do is today we create an oscillator, but out of minimum parts. So basically it's two capacitors and three transistors and around 5 resistors and a 6th resistor for the output stage, just to give the LED some front resistor to not put too much current through it. So we'll use 6 resistors, 3 transistors, 2 capacitors. And it's really easy. It looks complicated, but it's really easy once you draw it. And so let's start drawing. I got this idea, I mean it's a common idea, but I get this concrete idea from a book, and it's the Make Electronics by Charles Platt, 2nd edition book, Make Electronics by Charles Platt, very good book. This pretty circuit here is what I draw now is very challenging for beginners, but I will lead you through it, and there will be some exciting insights into a capacitor, the capacitor thing also. So Alan, to do with electronics now for a year, half a year, and I learned something new about capacitors I didn't even know before. So let's start. So what we have is some kind of voltage source. We have, let's say, here a positive terminal of the voltage source. And where we go is first to a 1K resistor, and from the 1K resistor we go right into a transistor, and that transistor is an NPN type. So let's draw it this way. I just realized that I have not often drawn NPN transistors in my life. And from here, we go straight to somewhere, most probably that will be ground here. But let's see, we can put that in immediately. Let's take it a little bit to the outside here. Negative, that's ground. Or minus plus and minus. And then we'll add another nifty little thing. So at the connection between the transistor and, oh, I realize I've drawn it wrong. So the emitter, it should go this way here, the arrow. So just imagine this is a straight arrow here, and here. Just your regular connection. And so we have the emitter down here. And yeah, then what we do is just in the interconnection between the transistor and the resistor, we have a little capacitor here. Make that very prominent because it's an important thing here. And that capacitor, it is also on the other end connected via resistor to the plus, to the positive terminal. And that resistor, it is 47K, so somewhat bigger resistor than the 1K. And yeah, and what we then have is a quite symmetrical situation. We have here again another 47K resistor and another capacitor and another 1K resistor. So this is 1K leading to a transistor. Let's time I get it right the first time. And the base lead of the transistor leads out here. And the emitter is again of this transistor connected to ground. So we have a very symmetrical situation here. And now comes the big clue. We connect the base of the left transistor to this corner here, and we connect this corner here where the capacitor and the resistor meet. We connect that to the second base of the second transistor here. And these two don't touch here. They look intersecting, but you can think of them not touching. There are no. So this is here through, and this is here through, and they don't touch. And okay, that's pretty much the thing. Not so complicated. Only 1, 2, 3, 4 resistors, 2 capacitors, 2 transistors, and then we have, so to say, our output here of the whole circuit. Quite interesting here. And there is this one, this resistor, which is around 100K. 100K resistor. And that resistor goes into the base of another transistor, our output transistor here, and we connect plus to that transistor, and then that's the real output now. So this is kind of the output of this right circuit here, and we'll talk once we get to the point where we understand what is output here before the 100K resistor. We're quite done. So all I draw now is just simply a thing for putting more current and more power to the output. So then this one here, and we go with this through, let's say, and now you can choose what do you want to drive with that circuit. And let's say we drive an LED. Because it's an LED, we need 470 ohm here in front of the LED, and then the LED itself. Because no LED can be connected directly to a voltage, because it would break them. And of course, yeah, this LED, it has to go back to there, to the negative terminal, and we just draw it like a second minus here. Let's just imagine we are connecting, these two are connected together, just two minus terminals there. Okay, so let's first look at this interesting situation. So we have 1, 2, 3, 4, 5, 6 resistors, like I said, 6 resistors. 1, 2, 3 capacitors, and 3 transistors, sorry, 3 transistors, and 1, 2 capacitors, just like I said before. And now the most interesting situation is what happens inside here, inside this, yeah, nearly square here, the components in here. That's the most interesting part, and we'll come back to what happens after the 1K then later. That is just pretty easy once we're done with the square in here. And the thing is, so imagine you connect up the plus and the minus, and so what's the matter here? What's starting? So let's imagine all transistors are like open switches. So open switches means not connecting through switches, so they block everything. There can be no current. So this one is open switch here, this transistor and this transistor, so no current flowing through them in the beginning. So the plus terminal, so this is all connected here at this point. So the plus terminal gets connected here, and instantly we'll have, let's say, what is this? Let's say this is plus 5 volt. And this is then consequently 0 volt, and we also have 0 volt here. So immediately plus 5 volt will be here at this joint, but no current flowing yet through this transistor because it is open. And so we're not looking at this part right now, we're only looking at the right part. No current flowing through this transistor, and also no current flowing through this transistor right here. And so there is plus 5 volt here, and I'll do that in color, I think. Let's start with the initial situation in light blue. So there will be 5 volts here, and 5 volts here, and after a very small amount of time. And so just imagine this disconnected for a while. And yeah, through this resistor here, to this resistor here, the first bigger resistor, this 47K, we can ask ourselves, okay, what's happening? So we have here a path of the 47K resistor. Okay, this capacitor, there's 5 volt on one side, okay, and then so what's continuing on the path? Okay, there is the base emitter, so and we can flow through to minus at this through this path here. And when we do that, there will be a voltage drop across the base emitter path here on the transistor of 0.7 volt. And yeah, and here will be 5 volt, and here will be then yeah, there will be everywhere 0.7 volt, and there are up here there are 5 volt, of course, everywhere. And once we get here, of course, we have 0 volt then, because that's all connected to ground. So just before the transistor at the base, we have 0.7 volt, all in here, and here we have 5 volt. And so if this happens, then this transistor is conducting. And now you ask me, okay, but what about the other 47K resistor? We also could say, okay, here is 5 volt, and then there's also a path here to ground, and then there could be also current flowing through here, and there also could be 0.7 volt here and 0 volt here. But the thing is, because we have here a resistor and a capacitor, there is a kind of a timed charging of this capacitor here, and also a time charging of this capacitor here. So in order to reach here the 0.7 volts that are needed to make this transistor go, the current go through this transistor, this capacitor has been loaded to 0.7 volt here. That's the effect of this capacitor. And as you know, if you are loading, because everything on this path here in between the resistor, the capacitor, and the transistor, every area here, every part of the conducting line has to be at 0.7 volts, so must be the right side of this capacitor. And for a capacitor to charge up to 0.7 volt, it's kind of like through a resistor, you have to first load it, and it takes some time. And this capacitor loading takes some time, and this capacitor loading takes some time. And one of them is first. One capacitor is loaded first, either this one here or this one. And let's just imagine this left capacitor was loaded first with 0.7 volts here. And if this is the first one, Then the other one is at some kind of potential, but it's not quite as fast on 0.7 volt. It's below 0.7 volt because this one was first 0.7 volt, and at this moment this one is not yet at 0.7 volt. And so this transistor charge starts to conduct first on the base emitter, and because of that, of the current through the base to the emitter, also this path here is opened. So the regular collector to emitter path of the transistor, because that's how a transistor works. Once you have current through the base to the emitter, then also the collector to emitter path starts conducting. And yeah, and what happens is now the second stage. So let's say, okay, this didn't quite make it as fast to 0.7. This capacitor was at 0.6 volt in blue. And of course, then we have also 0.6 volt here because there's the same potential at every part of the wire. And then this is of course at 0 still. So 0.6 to 0 are not quite reached 0.7, and that would be when this transistor would start conducting, but it didn't start conducting. This one I did first, so this transistor is conducting. And if this transistor starts conducting, now one very interesting thing happens, and let's put that in green. So when there is now current flowing through, because the transistor is now a closed switch where we can conduct, the 5 volts here, these are still 5 volts up here, and they go, let's take a lighter green, and these 5 volts, they go through this resistor and then straight, because that's now a closed circuit here, they go straight to ground. And you don't have your 5 volt here, you only have the 5 volt before the resistor, and after the resistor the voltage is dropped across the resistor, because now there is current flowing, and when there's current flowing through the resistor, the voltage is dropped. And let's if this is an ideal transistor, it has no resistance across collector and base. So when there is this current flowing, there is 0 volts all of a sudden here. And now the magic happens, because you have a change from 5 to 0 volt. Let's throw the delta in red. So this is, what is this 5 to 0 volts? This is minus 5 volts. Minus 5 volts happens here because suddenly there's current, suddenly there's a voltage drop. That's an immediate thing. So I've watched it, I built this circuit and I've watched it on this oscilloscope. Believe me, there's a voltage drop, an immediate voltage drop of minus 5 volt. Or a voltage drop of 5 volt. And the thing is, if you have a voltage drop of 5 volts downwards on the one side of the capacitor, guess what? You have a voltage drop on the other side of the capacitor, also of 5 volt downwards. And that's the miracle I discovered about capacitors. No matter if you have a change in voltage on one side, so it doesn't let constant potential or current through. That's always what they say about capacitors. But if you have a change, or a sudden change, or a gradual change in a capacitor, that change is, if that happens on one side of the capacitor, then that change also happens on the other side of the capacitor. And that's the big secret. And if you don't believe me, build circuits that prove me wrong. I guess you won't make it, because I proved it myself with the oscilloscope and all meters. You have also a minus 5 volt here at the other side of the capacitor here. And if you had before 0.6, as we said, then this sudden drop happens of minus 5 volt. You have 0.6 minus 5 volt, and you won't believe me, but now you have here minus, so 0.6 minus 5 is minus 4.4 volts. Suddenly, So, and I have to watch out because this is all referring to here, to the left side of this capacitor. You have here, there you have minus 4.4 volts on the left side of this capacitor. And you couldn't imagine it because your whole circuit, you have supported it with 5 volt here and with 0 volt here, and you cannot imagine, okay, how can something ever be minus 4.4 volt? Seems impossible. That's not in our supply voltage. But it happens, and I tell you, I have watched it on the oscilloscope. It's really minus 4.4 volt on this side of the capacitor. And so that's the winner situation. This capacitor was first charged to 0.7 volt. It led to the transistor drawing current then now to a conducting path. And that conducting led to a drop of 5 volt here, and that leads to a drop of 5 volt here. And now the small loser of 0.6 volt gets to be the big loser because now he is subtracted 5 volts additionally, and now he is at minus 4.4 volt. And because it's at minus 4.4 volt, at this point here at left of the capacitor, this base is not higher because it must be 0.7 higher than the 0, so it must be 0.7. And it is at minus 0.4.4, and this base is never conducting now. It cannot be conducting. So here we also have now minus 4.4 because there's the same potential at every place here. And what has to happen now is that this minus 4.4, what happens with it? That's a stable situation at first. But because we have a resistor here that connects to plus 5 volt, the plus 5 volt pushes current through this resistor to this negative, because minus 4.4 volt is a negative potential, plus 5 volt is a positive potential, so we have a potential difference, and there is current, positive current, like technicians want to see it, and it's quite correct every time. There is current flowing here to this transistor. And it's flowing, and it takes some time. As you know, current flowing through a resistor into a capacitor and building up the capacitor charge, that's called an RC network. So RC network, that's always the thing with resistor and capacitor, like this. And it takes some time, and if you choose the sizes of resistors and capacitor, I had here, to be precise, I had a nominal capacitor of 4.8 or 9. I measured then 4.9. So this is 4.9 microfarad. And this also was the same, 4.9 microfarad. To the left, you can't read, but it's the same, 4.9. And yeah, it takes some time. In my example, it has taken, I don't know how long that took. Yeah, it was like 300, one third of a second, 300 something milliseconds around. It takes around 300 milliseconds to charge this capacitor up here, then again through this resistor, and then this thing here, so that's the third phase, so to speak. Once we are charged up to 0.7, so now 0.7 here at the left of the capacitor, so, and also 0.7 here, then the same thing that started to the right here, that happens then to the left here, so 0.7. We were with the blue 0.7 here, now we are with the orange 0.7 we have reached here. And this transistor starts conducting, then there is a voltage drop of 5 volt here to then 0 volt here. Let's write that down, 0 volt at this junction here. And then 0 volt, and the current goes through the negative terminal through here. Meaning, if we have a drop of from 5 volt to 0 volt here, This means again 5 volt down. Then this 0.7 volt that was here before now drops here to minus 4.4 volt. Minus 4.4. I hope you can read it. And then if you have minus 4.4 here, then the base here, which is at minus 4.4, this transistor stops conducting, and you get immediately again 5 volt here, where you had before 0 volts. You have again then 5 volts on the right side. That's an upwards of 5 volt, and then there's for a short amount of time 5.6 volts to the left here. So actually a small correction. The capacitor tries to go up to 5.6 on the left, but when it rises and then it hits 0.7, and then it doesn't go above 0.7 much, because it goes slightly above 0.7, so 0.71 or 0.701 or something. But since then there is current flowing through the base emitter here to the left, in the left transistor, and so we won't go up to 5.6. We will stay at around 0.7 here. Just think of this picture of this 5.6 rewritten in 0.7. That's a mistake I noticed. I'm sorry for that. And so let's watch again to the left our transistor and the base emitter path. Base emitter is positive, above 0.7, and this still is conducting, of course. And what happens again is the game starts again. You have now here minus 4.4 volt, which needs to build up to 0.7 volts slowly over 300 milliseconds. And now this transistor is conducting, and there's 0 volt here. And then once you charged up this one to 0.7 volt again, then this one will be conducting again. And pulling low here, and this point here, and then if you pull it low, then again this transistor will be cut off, and you have a quite a change of cutting. If you look at one transistor, you have always the game of cutting a transistor off and then making it conductive, making it non-conductive, making it conductive, making it non-conductive, making it conductive. And so, yeah, that's the point here. And now we can watch the output stage here, what happens here. Because if you have 5 volts here, so let's watch this with 2 different colors. So one time you have 5 volts here, because if that transistor is non-conducting, the 5 volts stop here. You have here 5 volts. And if you have 5 volts here, then there is current flowing here through the base. So zack, to the base. If current is flowing through the base, then this transistor is conducting, and we have the LED lighting here. But if then there's a change in this transistor game to the left side, or looking only at this transistor, if we have then here, once this is conducting, we have here 0 volts. If there's 0 volts, then there's 0 volts at the base. This transistor is not conducting, so there's no current flowing through here, and then this LED is off. So it's the whole game of this transistor, this LED being first on, and then this LED being off. And so you have kind of one situation where you have at the output on, off, or 5 volt, 5 volt, 0 volt, 5 volt, 0 volt. And that is pretty amazing, because what you have just built is an on-off voltage level, which looks like this. First you are off, then you get to be on, and there again you are off, then again after a short period of time you are on, and so on and so forth, and on again and off. And what you have built is, so this is the This is the 5 volts level, and so this is the time here, time t. What you just built is an oscillation, voltage that goes high, low, or low, high, low, high, low, high, low. And yeah, you've seen that possibly from a 555 timer, but that here is much cheaper to build with a two transistors, 3 transistors, basically this inner part here, 1, 2, 3, 4 resistors, 2 capacitors, and 2 transistors. And yeah, that's about it. Thank you for watching, and if you like, subscribe or like or both, and then see you at the next video. Bye.